Welcome! Today, we'll explore problem number 1043, partition array for maximum sum. This is a fascinating problem that balances dynamic programming with array manipulation, giving us a chance to optimize our solution for maximum efficiency. Let's dive in. In this problem, we are tasked with partitioning an integer array ARR into contiguous subarrays, where each subarray can have at most k elements. The goal is to maximize the sum of contributions from each subarray. Each subarray's contribution is calculated as the maximum element in that subarray multiplied by the size of the subarray. Ultimately, we need to return the largest possible sum that can be obtained by partitioning the array according to these rules. The input consists of an integer array ARR and an integer k, and the output is a single integer representing the maximum sum. Let's explore how this works through examples to make the problem more concrete. Consider the first example, where ARR is 1, 15, 7, 9, 2, 5, 10, and k is 3. To achieve the maximum possible sum, we can partition the array into 3 subarrays. The first subarray is 15, 15, 15, which is formed by replacing the first 3 elements with the maximum value 15. This subarray contributes 15 * 3 equals 45 to the total sum. The second subarray is 9, 9, formed by replacing the next 2 elements with the maximum value 9, contributing 9 * 2 equals 18. Finally, the third subarray is 10, which has a single element and contributes 10 * 1 equals 10. Adding these contributions together gives a total sum of 45 plus 18 plus 10 equals 84, which is the output for this example. Now, let's take a look at the second example, where ARR is 1, 4, 1, 5, 7, 3, 6, 1, 9, 9, 3, and k is 4. In this case, the optimal partition divides the array into 3 subarrays. The first subarray is 4, 4, 5, 7, where the maximum value 7 is extended across 4 elements, contributing 7 * 4 equals 28. The second subarray is 7, 7, 9, 9, with the maximum value 9 extended over 4 elements, contributing 9 * 4 equals 36. Finally, the third subarray is 9, 9, 3, where the maximum value 9 contributes 9 * 3 equals 19. Summing these contributions results in a total sum of 28 plus 36 plus 19 equals 83, which is the output for this example. In the third example, ARR contains only one element, 1, and k is 1. Since there is only one element, no partitioning is needed, and the maximum sum is simply the value of the element itself, which is 1. Turning to the constraints, the array length can range from 1 to 500, and the values in the array can go up to 10⁻⁹, so efficiency is critical when designing the solution. Some important edge cases include single-element arrays, where the output is the value of the element, and scenarios where k equals the array length, allowing the entire array to be treated as one subarray. Additionally, if all elements are the same, the result is the sum of the entire array. It's crucial to account for these cases to ensure the solution is robust and handles a wide range of inputs effectively. To start, one approach we might consider is a brute force method that explores all possible ways to partition the array. The intuition here is straightforward. For every possible way to divide the array into subarrays, we ensure that each subarray has at most k elements. Then, for each partition, we calculate the contribution of each subarray by identifying its maximum value, multiplying that by the subarray length, and summing these contributions. Finally, we return the largest sum out of all the partitions we evaluated. However, while this approach is conceptually simple, it's computationally expensive. The number of ways to partition the array grows exponentially as the size of the array increases, leading to an exponential time complexity. This makes the brute force approach infeasible for larger inputs, especially when n is large. That's why we need a more efficient solution for this problem. A more efficient approach is to use dynamic programming with a bottom-up state transition. The key intuition here is that we can break the problem into smaller, overlapping subproblems and build the solution incrementally. Instead of exhaustively exploring all possible partitions, we focus only on the maximum sum achievable for each prefix of the array by evaluating the last k elements at a time. This works because subarrays are constrained to have a maximum length of k. To do this, we define dp, I, as the maximum sum achievable for the first I elements of the array. For each index I, we examine all possible subarrays ending at I with lengths ranging from 1 to k. For each of these subarrays, we determine its maximum value, compute the sum it would contribute, and add it to the optimal sum for the preceding elements, represented by dp, ij. By updating dp, I, with the best sum found, we ensure we are building the solution efficiently. At the end, dp, n, will hold the maximum sum for the entire array. The computational efficiency of this dynamic programming approach is one of its biggest strengths. In terms of time complexity, it takes n*k, because we iterate over the array once and evaluate up to k subarrays for each element. The space complexity is n, as we only need to store the dp array containing the maximum sums for each prefix. This approach was chosen because it strikes an excellent balance between clarity and efficiency. By leveraging the problem's constraints, specifically the limit on subarray size, we eliminate the need for redundant computations. This makes the method significantly faster than the brute force approach while remaining easy to implement and understand. Furthermore, the optimized DP approach scales well for larger inputs, making it practical for the problem's constraints, such as n up to 500. There are a few trade-offs to consider with the dynamic programming approach. First, while it is efficient, it does require additional space to store the DP array. However, given the problem's constraints, this space requirement is reasonable and manageable. Another assumption the algorithm relies on is that finding the maximum value in a subarray of length k is inexpensive. This assumption holds because k, the maximum subarray size, is relatively small compared to n. Overall, this solution provides an effective balance between optimality, efficiency, and simplicity. It avoids the exponential growth of the brute force approach while ensuring the correctness of the result. These factors together make the dynamic programming strategy the ideal choice for solving this problem. To solve this problem, our goal is to partition the given array into subarrays, ensuring that no subarray exceeds a maximum length of k. The objective is to maximize the sum of the maximum values in each subarray. To begin, let's consider the brute force approach. The intuition here is straightforward. We generate all possible valid partitions of the array, where each subarray has a length of at most k. Then, for each partition, we calculate the sum of the maximum values in its subarrays and return the largest sum among all partitions. For example, if we have an array 1, 15, 7, 9, and k equals 2, some valid partitions would be 1, 15, 7, 9, or 1, 15, 7, 9. Once these partitions are generated, we compute the sum of the maximum values from each subarray. If we take the partition 1, 15, 7, 9, the sum would be max 1, 15 plus max 7, 9 equals 15 plus 9, which equals 24. While this approach guarantees correctness, it is computationally intensive due to the sheer number of partitions that need to be evaluated, especially as the size of the array grows. To handle this, we can maintain a variable to track the maximum sum across all partitions. As we evaluate each partition, we update this variable whenever we encounter a partition with a larger sum. Once all partitions have been examined, we simply return the value of this variable as our result. However, to improve efficiency, we turn to dynamic programming. The optimized approach leverages the idea of systematically calculating the maximum sum using previously computed results. Here, we define a state dp, I, where dp, I, represents the maximum sum achievable by partitioning the subarray ARR, 0 I plus 1. The base case is simple. For a single element, dp, 0, is just the value of that element, ARR, 0. The transition step involves iterating through the array and considering all possible subarrays ending at a given index I, ensuring that the length of any subarray does not exceed k. For each subarray, we calculate its maximum value and use it to update dp, I. This systematic approach replaces the need to evaluate all possible partitions explicitly, drastically improving efficiency. The update formula for dp, I, ensures that we account for all valid subarrays ending at I without exceeding the length constraint. Specifically, we use the relation dp, I, equals max, dp, I, dp, j1, plus max, r, j I plus 1, where j ranges from max, 0, ik plus 1, to I. This ensures that we only consider subarrays of valid length while updating dp, I. Ultimately, the value of dp, n1, where n is the length of the array, gives the desired result. To understand this better, let's take an example with ARR equals 1, 15, 7, 9, 2, 5, 10, and k equals 3. First, we initialize the DP array with zeros. For the first element, DP 0 equals 1, as there's only one element. For I equals 1, we evaluate subarrays like 1, 15, and find that DP 1 equals 30 using the maximum value of the subarray in prior results. Similarly, for I equals 2, we consider subarrays 1, 15, 7, and others, systematically updating DP I. By the end of the process, DP len RR-1 gives the final result, which in this case is 84. This dynamic programming approach offers several key advantages. First, it avoids redundant calculations by storing intermediate results in the DP array, which can be accessed in constant time. Additionally, by limiting the range of subarrays to a maximum length of k, we significantly reduce the computational overhead. It's also important to consider edge cases. For instance, if k is very small, like k equals 1, each element forms its own subarray, and the result is simply the sum of the elements in the array. On the other hand, if k is very large, such that k is greater than or equal to the array's length, the entire array forms a single subarray. In terms of implementation, we use a DP array to store the maximum sums for subarrays up to each index, which is both space-efficient and quick to access. The time complexity of this solution is n*k, where n is the length of the array, as we iterate through the array and evaluate up to k subarrays for each index. The space complexity is n, accounting for the DP array. This balance between time and space efficiency makes the dynamic programming approach far superior to the brute force method for solving this problem. This Python implementation solves LeetCode problem number 1043, partition array for maximum sum, using dynamic programming for optimal efficiency. The goal is to partition the array into subarrays of at most k length and maximize the sum of the maximum values in each subarray. The maxsum after partitioning function begins by initializing an array DP of length n, the size of the input array ARR, with zeros. The DP I value represents the maximum sum achievable by partitioning the subarray ARR I plus 1. The outer loop iterates over each index I in the array. For each index, it calculates the maximum value of subarrays ending at that index, with lengths ranging from 1 to k or the length of the current subarray, whichever is smaller. The inner loop iterates over possible subarray lengths j from 1 to min, k, I plus 1. The maximum value, max_val, within the current subarray is tracked dynamically. For each subarray length j, the algorithm computes the sum of the maximum values, considering the contribution of the current subarray, max_val *j, and the maximum sum achievable from the previous partitions, dp ij. Finally, dp I is updated with the maximum of its current value or the calculated sum for the current partition. After iterating through the entire array, the result is stored in dp-1, representing the maximum sum achievable for the entire array. This approach efficiently calculates the solution in n*k time, where n is the length of the array. The space complexity is n for the DP array. It ensures that the solution is optimal by exploring all valid partitions without redundant computations. This is the Java implementation of LeetCode problem number 1043, partition array for maximum sum. The logic mirrors the provided Python solution, with key differences such as using explicit type declarations, following Java's class structure, and handling arrays. The implementation uses dynamic programming to calculate the maximum sum by iterating over the array and considering partitions up to size k while maintaining the maximum value in the current partition. To solve this problem, we use a dynamic programming approach. First, we initialize the length of the array, n, to 7 since the input array has 7 elements. We also create a DP array filled with zeros, which will store the maximum sum we can achieve up to each index. Now, in the outer loop when I is 0, we start by initializing max_val to 0. The inner loop runs from 1 to k or until the start of the array. For j equals 1, we calculate max_val as the maximum of the current max_val and ARR, 0, resulting in 1. Using this value, we update dp, 0, to the maximum of its current value and the sum of max_val *j, which gives us 1. At this point, the DP array becomes 1, 0, 0, 0, 0, 0, 0, signifying that the maximum sum achievable for the subarray ending at index 0 is 1. Next, for I equals 1, we reset max_val to 0. In the inner loop, when j equals 1, we calculate max_val as the maximum of 0 and ARR 1, which is 15. We then update dp 1 to the maximum of its current value and dp 0 plus max_val asterisk j, resulting in 16. For j equals 2, we extend the subarray and find max_val remains 15, so we update dp 1, again based on the longer subarray, resulting in 30. The DP array becomes 1, 30, 0, 0, 0, 0, 0. Moving to I equals 2, we again reset max_val and iterate. For j equals 1, max_val becomes 7, updating dp 2 to 37. For j equals 2, we extend the subarray and find max_val increases to 15, but the maximum sum remains 37. Finally, for j equals 3, we again use a larger subarray and update dp 2 to 45. The DP array now becomes 1, 30, 45, 0, 0, 0, 0. Finally, for I equals 3, we follow the same process, and the result for this index becomes 54. Now, continuing with the outer loop, for I equals 4, we repeat the same sequence of calculations. By considering subarrays of different lengths up to k, we determine that the maximum sum for this index is 57. Similarly, for I equals 5, we find that the maximum sum is 62, and for I equals 6, the maximum sum becomes 72. As we complete all iterations, our final DP array is 1, 30, 45, 54, 57, 62, 72. The result for the entire problem, which is the maximum sum of the partitioned array, is stored in DP 6, giving us an output value of 72. In this second example, we apply the same logic to a new array, RR equals 1, 4, 1, 5, 7, 3, 6, 1, 9, with k equals 4. We initialize n to 9 and create a DP array of size 9 filled with zeros. As we iterate through the array, we calculate the maximum sums for each index using subarrays of lengths up to k. For instance, at I equals 4, the maximum sum achievable is 28. By the time we reach I equals 8, the end of the array, the DP array has been fully populated, and the maximum sum stored in DP 8 is 84. This value is our final output for this example. Finally, in this third example, the input array is much smaller, ARR equals 10, 20, 30, and k equals 2. Here, we initialize n to 3 and create a DP array of size 3 filled with zeros. Starting with I equals 0, we calculate DP 0 as 10. For I equals 1, we consider subarrays of length up to 2 and find that DP 1 becomes 40. At I equals 2, using the same approach, we determine that the maximum sum is 60. Since the array ends here, the final output for this example is 60. Here, we analyze the time complexity of the solution. The solution involves two main loops, an outer loop that iterates through the array and an inner loop that processes up to the last k elements for each index. The outer loop runs from 0 to n1, where n is the length of the input array, contributing an O(n) factor. For each iteration of the outer loop, the inner loop runs up to k times in the worst case, depending on the value of k in the current index I. Inside the inner loop, the operations such as updating max_val and dp I are constant time operations, each taking O(1). Therefore, the inner loop contributes O(k) per iteration of the outer loop. Combining these, the total time complexity of the solution is O(n*k). To summarize the time complexity, the outer loop runs O(n) times, the inner loop runs O(k) times for each iteration of the outer loop, and the work done inside the inner loop is O(1). Multiplying these contributions gives us a total time complexity of O(n*k). Now, moving to the space complexity, the solution primarily uses a dynamic programming array DP to store the maximum sum results for each index. The size of this array is n, where n is the length of the input array, resulting in O(n) space usage. Additionally, scalar variables such as n, max_val, I, and j require only constant space, contributing O(1). Since no other data structures are used, the overall space complexity is dominated by the DP array, making it O(n). The space complexity remains O(n), because the DP array is the only significant data structure used, and its size is proportional to the length of the input array. To understand the efficiency of this dynamic programming approach, let's compare it to a brute force solution. A naive brute force approach would involve generating all possible partitions of the array and calculating the sum for each partition. This would result in an exponential time complexity of O, k to the power of n, where k is the partition size and n is the length of the array, making it highly inefficient. In contrast, the dynamic programming solution takes advantage of overlapping subproblems and the optimal substructure property to reduce the time complexity to O(n*k) and the space complexity to O(n). This optimization makes it far more practical and scalable for larger inputs. Now, let's break down the best, average, and worst-case scenarios. In the best case, when k equals 1, the inner loop runs only once for each iteration of the outer loop. This simplifies the time complexity to O(n). In the worst case, when k is large and close to n, the inner loop runs up to k times for each index, resulting in a time complexity of O(n*k). The average case also yields a time complexity of O(n*k), as the inner loop's iterations depend on k. Mathematically, the total time complexity arises from the outer loop running n times and the inner loop running up to k times, with constant time operations inside the inner loop. Combining these gives O(n*k). The space complexity remains O(n) due to the DP array, and no additional data structures contribute significantly. This analysis confirms that the dynamic programming solution is both time-efficient and space-efficient compared to brute force approaches. When solving this problem, there are several common mistakes to be aware of. First, not considering edge cases can lead to incorrect results. For instance, if the array has fewer elements than the given k, or if all the elements in the array are the same, these scenarios can behave unexpectedly if not explicitly tested. It's important to identify and handle these edge cases upfront. Next, relying on an inefficient brute force approach can slow down your solution significantly, especially if you recalculate maximum values for overlapping subarrays multiple times. Instead, think about how you can optimize by pre-computing values or avoiding duplicate work. Another frequent mistake is misunderstanding the constraints around k. Remember, the problem typically allows subarrays of size at most k, not exactly k. Misinterpreting this can lead to wasted effort or incorrect logic. Overcomplicating the dynamic programming solution is another pitfall. Focus on defining the state clearly. What does dp I represent and how can you transition between states optimally? Finally, if you're working in a language like C++ or Java, be mindful of integer overflow when dealing with large arrays or values, as this can lead to unexpected issues in your solution. Now, let's discuss some key insights that can help you tackle this problem effectively in an interview setting. Recognizing patterns is crucial. This problem is essentially a combination of sliding window techniques and dynamic programming. Whenever you're tasked with dividing an array into subarrays under constraints, it often hints at a DP solution. Additionally, this problem exhibits what's called optimal substructure, meaning the solution to the overall problem can be built from solutions to smaller subproblems. This is a hallmark of dynamic programming and should guide your approach. It's also worth noting the trade-offs between different methods. While brute force might be acceptable for small inputs or during the exploratory phase, interviewers generally expect you to propose optimized solutions that scale well, such as using DP or sliding window techniques. Lastly, clear communication is critical. Be sure to articulate your thought process, why you're using dynamic programming instead of brute force, for example, or how your chosen approach handles edge cases and constraints efficiently. This not only demonstrates your understanding but also shows your ability to think critically about problem solving. Another way to deepen your understanding of this problem is by exploring related problems, as they often share underlying techniques or patterns. For example, LeetCode 1043, Partition Array for Maximum Sum, is the problem we're discussing and represents a classic example of partitioning for optimization. LeetCode 312, Burst Balloons, is another partitioning problem but with a twist. It focuses on maximizing value through overlapping intervals. Similarly, LeetCode 714, Best Time to Buy and Sell Stock with Transaction Fee, also involves maximizing profit under constraints, making it a good exercise in dynamic programming. Finally, LeetCode 53, maximum subarray, is a simpler problem that's directly related to finding optimal sums within an array. By practicing these problems, you'll start to see recurring themes and techniques, which will make it easier to recognize and solve similar challenges in the future. When considering alternative approaches to this problem, each comes with its own trade-offs. The sliding window technique can be a great option when subarrays must be contiguous, as it avoids redundant calculations and improves efficiency compared to brute force. However, sliding window is less effective when the problem involves arbitrary partitions that aren't strictly sequential. Dynamic programming is often the optimal approach for this type of problem. It provides scalability, with a time complexity of n*k, where n is the size of the array. The trade-off here is higher space complexity, as you need to store intermediate results for each state. Finally, while greedy approaches might be tempting for simpler versions of the problem, they often fail when more complex constraints are introduced. If you do consider a greedy method, make sure to rigorously validate its correctness, as it's not always guaranteed to yield the optimal solution in problems of this type. Great job! To summarize, we tackled the problem of partitioning an array for maximum sum using dynamic programming. We discussed its time and space complexity, and highlighted key takeaways like the importance of breaking down problems into subproblems. Thank you for watching, and stay tuned for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!